So hello everyone. Oh, there is echo again. What is the problem? Hello. Yeah, now it's fine, I think. Okay, so welcome to the fifth class. Fifth tutorial of the course PH 28 Introduction to Classical Mechanics. So today we will do some. I do not say problems. We will do some theoretical development of uh, central force and a few problems on the uh, moment center of mass or center of momentum frame on the center of mass frame. So okay, so let us start. First we will do something related to the central force. Okay, so as you have already shown in such lecture that if I have two different mass and if they are separated by a distance r, where r is actually r1 minus r2, and if o is my uh, point of observation, then this is r1 vector, this is r2 vector. Now in this way we can construct the geometry of our problem with vectors. And if we introduce the center of mass frame, which is m1 r1 plus m2 r2 by m1 plus m2, these are vector. This already you have shown, and we have also defined a quantity which is mu, that is called the reduced mass. So using these two thing, that capital R and this reduced mass, we can reduce a two body problem into a one body problem with a mass mu, that you have already seen. That for this problem we can write our kinetic energy in terms of this capital R and this mu, where capital M is actually the m1 plus m2. So we are treating the problem like there is a mass capital M which is sitting at the center of mass position, and there is another mass which is the reduced mass mu, and the separation between that m1 and m2 is small r. So also, as we can neglect this term from the kinetic energy, because that mr dot is actually constant. So when we will go to form our equation of motion, this first term will not contribute. That's why effectively we can write our Lagrangian by eliminating that first term. It is the total kinetic energy term. Oh sorry, there is a dot on r dot square minus the potential energy. Yeah, this you have already seen. And if we are uh, considering a motion in a plane, then in a this type of system where it is the r and the distance is phi, so two coordinate r and phi, plane polar coordinate, then that r vector can be written as r dot square plus r square phi dot square minus vr. Okay, this already you have seen. Now from here we can also find the equation of motion using the Lagrangian equation. So that will be like this: del v del r is equals to 0. This is for the earth part, r component, and for phi component that will be mu r square phi dot equals to 0, which gives you mu r square phi dot is a constant. And if you look at this term carefully, this is actually the angular momentum in the polar coordinate. So that is actually L, which is our angular momentum. So it is saying that L is constant, that means L vector, that means dl dt is equals to 0, which will tell you that d dt of r cross p is also equals to 0, where r is the radius and p r is the distance and p is the momentum. So by this analogy you can say that our motion will be always in the plane which is perpendicular to the angular momentum of that particular system. So if the motion is in this plane, then the angular momentum will be perpendicular to the plane. So our motion will be confined in a plane. This is all you have seen. Now from here you can write the total energy also here, and if you put this L, well, it is called small l as noted by the book which I follow actually. So it can be written as 2 mu r square Vr. Okay, and this part we call this at V effective, that is the effective potential. Okay, so V effective R. Okay, oh, sorry, I have written me. Okay, so this is how we can construct the solution of a two body problem. I mean two bodies separated by a distance, and the only force acting on the system is the central force, that may be the gravitational force or the electrostatic force, that is which is proportional to the distance only. I mean 1 by distance square. Now some approximation we will do here. So suppose we have defined mu is equals to m1 m2 by m1 plus m2. Now for a solar system, I mean earth and sun like system, let it be perfectly elliptical, and the sun is here and the earth is here, it is rotating around the sun. But if it is m1 and m2, but for this particular case the mass of sun is very large than the mass of earth. So m2 is very greater than m1. This is the sun. Okay, so what happens in that case? So m1 m2 okay, 1 plus m1 by m2. Okay, now as m2 is very large, greater than m1, that means 1, or you can say m1 by m2 is very less than 1. So that's why we can neglect this particular term in the denominator, and m2 will cancel out. So this will give you m1 effectively. So for this system, when the mass of sun is very large than the mass of earth, then the mu, we can replace the reduced mass of this earth sun system by the mass of the earth only, which is m1. So if we use this approximation for this particular problem, then this equation, this expression or this equation, that can be written as equals to half m r dot square plus l square by 2 m r square plus Vr, where I have just replaced the mu by m. So this is a very important result, because generally for we deal with solar system like problems in central force, and in that case one mass is very larger than other mass, and that's why we use this approximation where m is the mass of the lighter object. Okay, so this is an approximation. Okay, now another thing related to this. Okay, now I have told you that V effective R is actually Vr by plus L square by 2 mr square or mu r square, whatever I was, 2 mu r square. And if it is this type of system where m2, where the one mass is very high, then that is Vr plus L square by 2 mr square. So don't confuse, I will repeatedly use L and L, this is the same. Sometimes I use small l and sometimes capital L, no difference, that is same for this class. Okay, okay, So now if you know that our force, that is gravitational force, is like minus k by r square, whether it is gravitational or electrostatic. So this same problem which I told you, sun and earth system, it is also applicable for the nuclear, for a particular nucleus, because the mass of a nucleus is much more greater than the mass of an electron. So the mu can be replaced as the mass of the electron only for that problem, and because the nucleus is very much heavier. So the same thing. So if we take Fr equals to minus k by r square, that is gravitational force or electrostatic force, then this, from this you will get the V effective as minus k by r plus L square by 2 m r square. And if you plot, you have already seen that it will give you this type of structure, and you, with various energy, you have calculated which will be the bounded motion and which will be the unbounded motion. So I will not go into that. I will go into another force. Now suppose if your Fr is equals to minus k by r cube instead of minus k by r square, then what will happen to this particular picture? So if your Fr is minus k by r cube, then you can write, you can plot, okay, V. Okay, so let it be Vr, not the Fr. Potential is minus k by r cube. Whether here the potential was minus k by r, only the potential part, not the angular momentum part, which is the second part. So this part is always here. So from Vr minus k by r cube, if you calculate V effective, that part is always there, L square by 2 m r square. Okay, so if you plot this potential, this will take like this. Okay, so this will be the minus k by r cube, and this will be the L square by 2 m r square thing. So if you join these two, then you will get a plot like this. It will not cross, sorry, okay, like this. Okay, so it will, you will get a plot like this. It is the plot of L square by 2 m r square plus minus k by r cube. So what happens in this particular problem? That is interesting. So suppose in the previous case, if you have the energy, this red line, say that is E1. So for this particular region from here to here, your energy is greater than the potential energy, and you know that our half m r dot square, that is kinetic energy, that is the total energy minus V. So E minus V should be always positive for a physical motion. It cannot be negative because r cannot be negative. So for this particular case, if you have the energy, total energy E1, your motion will be bounded within this radius. Okay, suppose R1 and R2. But in this case, when your potential goes like minus k by r cube, and if you have a energy like this, then what happens? You can see this in this particular region, your potential is greater than the energy. So particle cannot be bounded in this region because it cannot penetrate the potential. So whereas in the first case, the bounded motion was between r1 and r2, in this case the bounded motion will be, if r less than r1, that means this region, and if r greater than r2, that is this region. Okay, so these two region, then the motion can be is possible, but within the r1 and r2 the motion is not possible due to the because the half m r square would be negative. Imagine, so r is imaginary. So the so I think you can see the difference, that for just the shape of the potential has been changed. So your condition for the bounded motion has been changed a lot. Previously it was between r1 and r2, but in this case there is no motion between r1 and r2. Only the possible motion is if it is less than r1 and if it is greater than r2. So this is how the motion, I mean the bounded motion or the unbounded motion, that will change depending on the potential, given potential, because your L square by 2m square m r square term is always constant. The only factor which changes the motion is the first factor, which is the given potential. It can be different for different things. So this I wanted to discuss with you. Now now we will do one problem that will help you to solve your assignments also. Okay, so suppose I have a particle and I have a potential, this type of potential, say it is y, it is r, it is one dimensional, so r is just one dimensional vector, and let the potential is like a r to the power 4. Okay, now what will happen around this stable point? So the equation we can write it as, oh, why I have written is y, it can be v, yes, the potential. So Vr has a form of a r to the power 4. Now we will write the now we will try to find out what will be the time period for this particular problem, and it is a one dimensional problem. Okay, so your half m r dot square, it is the kinetic energy plus the potential energy, that is equals to the total energy of the system. Okay, now is E minus Vr. So we assume that the mass of the particular object is unity. Okay, that's why we will write just m is 1, and your, in that case, your r dot square will be 2 e minus Vr. Okay, then r dot is equals to 2. If I am doing anything wrong, please tell me this. Okay, so r dot is dr dt, that is a minus Vr. Okay, now dr by 2 e minus Vr root over, it will give you the time period. Okay, now let us equate the, I mean let us take the lower limit of r as 0, which is here this position, so 0. So what will be the maximum value of, I mean the upper limit of r? So from this equation you can see at the upper limit of r the velocity is 0, because suppose it is the energy E. So when the particle will reach this point, this particular point, then it will again move backward to the stable point O. So at this particular point the velocity must be 0, then it will take the backward motion and it will come again towards the O. So if velocity is 0, that means r dot is equals to 0. So you can write V is equals to E. Okay, and your V is given as a r to the power 4. So from here you can write that r max is actually E by a to the power 1 by 4, right? So this is your maximum limit of r, E by a to the power 1 by 4. Now you can see that here I have taken from 0 to this point, but this will not give you the time period. The time period will give, I mean by multiplying this time with 4, because if you start from here you have to come at this particular point again with a full I mean after a full oscillation, that will give you a time period. But as the problem is symmetric, you can find your time period using this particular patch of the path also, only the portion which is in the first coordinate. So that is due to the symmetry, because what time it will take from going to this path, it will take the same time from going to this, suppose a to O and B to O. So you can multiply with the appropriate factor only. So now if we do this particular thing, then the integration becomes like, let's say this is t, so 0 to e by a 1/4 tr to e minus vr is equal to a r to the power 4. So let me write that minus this one. Okay, just a second, what happened, just a second. Okay, yeah, so I have some problem with that. Yes, so this is how you can calculate your time period of that particular system. Now we will do that 1 by root 2. Now dr, we will take e common, so 1 minus a r to the power 4 by e. Right. Now forget about this term, I am writing proportional sign, no problem in that. I just want to show you the dependency of the time period. That's why I have absorbed that 1 by root 2 and I have just replaced the equal to sign by the proportional sign. So here if you assume a r to the power 4 by e is equals to x, then you will get a by e 4 r cube dr equals to dx. That means your dr is dx by a by e 4, and r cube we will write as e by a to, yeah, there will be x. Okay, so from here dr is dx by a by e 4, r cube means e x by a to the power 3 by 4 coming from here. So this is how you can replace your dr. So that I will do, I need a big place, yeah. So dr is dx by 1 minus x, and here this term e by a 1 by 4 e by a 3 by 4 times x to the power 3 by 4. I have just replaced this in this particular term, so you will get this. Okay, now and your limit will change accordingly. So your r max was e by a to the power 1/4. If you put your r max in this particular value, then you will get x max is equals to 1 and x min equals to 0. Okay, so this is half e by a 1 by what happened, sorry, can you see my screen? Something happened to it. Yeah, now it is fine. Okay, now 1 e by a is here 3 by 4, and all the other term dx by 1 minus x, and there was a 4 also, I think. Okay, now the point I was trying to make is that it will give you a numerical value. Okay, if you do the integration, so that will give you the value, but your time period, that will be proportional to 1 by e to the power half and e to the power 1 by 4th. So I have cancelled this e by this e to the power 3 by 4th, so which will give you 1 by e to the power 1 by 4th. Okay, so t is going as e to the power minus 1 by 4th. Okay. So you can see that for this particular potential, when the Vr was given as AR to the power 4, your time period of the system that is scaling as e to the power minus 4. Now suppose instead of E you have a particle which have energy of Ne. So if instead of E your energy is n times E, then how it will affect the time period of the system? So what will happen then it will be proportional to n e to the power minus 1/4, that is t varies n to the power minus 1/4 e to the power minus 1/4. Okay. So you can see your time period is decreasing by a factor of n to the power minus 1 by 4. I mean, I think you can understand. So suppose if you say t equals to t1 and it is t2, then your t2 by t1 will be proportional to n to the power minus 1 by 4. That means your time period t2, which is associated with the higher energy of Ne, where n is greater than 1, then your time period is decreases as that time, that n, which is how many times of the previous energy is the current energy, to the power minus 1 by 4. So remember that. And if you can do a simple problem with Vr equals to AR to the power square also, and you can find the dependency on time period, dependency of time period on the total energy E. So I will ask you to do a simple problem like this. The main problem is you have to make this particular form as a dimensionless quantity, which I have taken as AR to the power 4 by E as x, and I have made the integration as a dimensional integration, which will give me a numerical value only. Then I can tell how the time period is dependent on the E, because in this integration there is no E time. Okay. So okay. So any question till now? Okay. Good. Now, yeah, now we will do one thing. So, okay. So for the central force, you have seen that, and in that regime, that one mass, the central mass is very much greater than the mass which is revolving or moving around that heavier mass. There the energy is half mr dot square plus L square by 2 mr square plus Vr, and the Lagrangian is mr dot square minus so L square by 2 mr square minus Vr. Okay. Now and where this is the V effective. Okay. Now one thing we will do that, a particle which is moving towards the massive particle, and suppose the force is k by r square force. Okay, and the potential is k by r. So you can write this particular system's force which is acting, I mean acceleration, the equation of motion. I am doing it in a different way, not going through the starting from the Lagrangian. You can also reach this particular thing which I am going to write using Lagrangian. So your equation of motion will be like this: Fr plus, so I will not, so your acceleration, this will be equal to the force. This is your that's just Newton's law, that acceleration is equals to force. Now here the force will be ddr of V effective. Okay, dvdr is force, you know, that is ddr of V plus L square by 2 mr square. So this is your equation of motion. when a particle is moving radially towards a massive particle under the influence of a central force, I mean minus k by r square type force. Now I will take the help of the book for this particular thing. Yes, so this is your equation of motion. Now one thing we will do, we will replace u as 1 by r. So the r is the radial distance. So if you do this substitution, then you will get dr dt as minus 1 by u square du. I mean it is a chain rule. Okay, let me write. Dr dt is dr du dt. Okay, now if you use this, your del r del u dr du becomes 1 by u square, and du dt we will write as du d phi dt. Another chain rule is here. So that means minus phi dot by u square du d phi. So remember this, u is actually the inverse of the radial distance. So it is minus r square phi dot, you can write it in this way also, just replace the u by 1 by r. Okay, and as you know already that my angular momentum, that is m r square phi dot, so r square phi dot is actually L by m. Okay, and we can replace it here, minus L by m du d phi. Okay. This is my dr dt. So dr dt is minus L by m du d phi. Now similarly just do it, the d2r dt square. So you will get it. It is just chain rule, apply that and you will be able to do it. So L square u square by m square d2u d phi square. Okay, so your d2r dt square is this and your dr dt is that one. Okay, so now we will put these two form which we got in the main equation, I mean the equation of motion, which was this one, mr double dot is equals to minus ddr v plus L square by mr to mr square. So we will just replace r double dot, that is d2r dt square, by what we have already what we have got here. So we will just replace it. So if you just replace it, that was m r double dot, that means this total expression d2u d phi square, that is equals to minus del r v, just a second. Yeah, so del r and del r we will replace by del u. So if you replace all the thing accordingly, then you will get the total equation as L square u cube by m is equals to f1 by u. Okay, now you can ask where this f is coming from. Okay, so this f is nothing but this one, this combining two time. So I have written fr as minus del v del r. As you know, this is the force. Okay, so this del v del r is fr, and as I am writing every r, I am replacing every r by u. That's why I have replaced that r is to u in this particular expression also. So instead of f of r, you will get f of u. So that f of 1 by u, okay, because this f of 1 by u is similar to f of r. And if you do the differentiation with the second term, that will give you a 1 L square by 2m r cube. I think you can understand, this 2 will give you L square by 2m r cube, and if you put r as 1 by u and L as your m r square phi dot and replace everything in u, then you will get this term. So I am not doing this, you can do it by yourself, it is a very simple thing. So if you do this, then you will get a equation, okay, 1m will be here and minus L square U cube by M 1 by U. That means d2u d phi square plus U is equals to minus M by L square U square f of 1 by U. Okay, it is f. Yes, so this is a very important expression. This, by solving this particular thing where U is 1 by R, you can get the the trajectory of that particle. So this equation with your particular form of the force, that is Fr or F1 by U, whatever, that will tell whether your motion would be in circle or in ellipse or in hyperbola, because you know that the motion generally in central force obeys this type of conic section. So what type of conic section your particular problem, a particular mass or point mass will follow, that will come by solving this particular equation. Okay, so I think sir will do it in the next class, how you can find the equation from given potential by using that central force method. So you can do that. Okay, so now any problem till now? So have you understood how this term is coming, or I should do it? I think you can do, just differentiate that. I am writing very in a small way, L square by 2m R square. Okay, that will give you L square by R cube. All the terms are there also, and replace this L by m R square phi dot and this R by 1 by U. Again take this whole expression into 1 by U or R, then you will get this particular expression. No problem, you will not face any problem in that. Okay. So this is the important equation of central force problem. Okay, now okay, so all other problem, other theoretical background, we will do it in next class, because you have to know about the equation of conic section that sir will cover, I think. And now we will go to some problems on the center of mass frame. It is very important thing in physics. So for that two body problem, you can see that R1, R2, R. So for this particular problem, we have defined that M1 R1 M2 R2 by M1 plus M2. So this was the actually this was the position of center of mass for that particular system, and this method is applicable in various problem in classical mechanics. So I will show some of you some of the problems. Just a second. Lagrangian. Okay, yes. Now let us go to a particular problem of collisions. So to deal collision problem in center of mass frame is very easy, and you can see why. Okay, so now suppose there is two mass V2 and V1. Two mass M1 M2 which are moving with velocity V2 and V1, and if you calculate the center of mass frame, so this will be the center of mass frame, and capital V is the center of mass velocity of this system of problem. So capital V is actually M1 V1 M2 V2 by M1 plus M2. It is exactly same as the center of mass coordinate, that is R M1 R1 plus M2 R2 by M1 by R2. and it is the in the velocity it is the velocity of the center of mass v. Okay, so that this vector is v and this is v1 by v2. So if you calculate the velocity of mass 1 with respect to the center of mass, so this v1 v2 all this was with respect to lap frame. Now from lap frame we will go to the center of mass frame. So if v1c is the velocity of first particle in the center of mass frame, that will come from v1 minus v, right, because this is the velocity of the mass 1 with respect to the center of mass frame. Okay, so and your v1 minus v is m1 v1 m2 v2 by m1 plus m2. If you do this calculation, you will get m2 by m1 plus m2 v1 minus v2. All these are in factorial notation. Okay, yes, so this is your velocity of mass 1 with respect to the center of mass frame. Similarly, if we want to calculate the v2c, this is the v2c and this is the v1c. So let me write it that it is v2c and it is v1c. So your v2c will be v2 minus v from the geometry, so that will give you like this, v1 minus v2. So you can see that your v2c and v1c, these are oppositely directed. It was positive and it was negative, all the expressions are same, so they will move exactly opposite to one another in the center of mass frame, not in the lap frame, because it is clear that in the lap frame they are not oppositely directed, but in the center of mass frame it is oppositely directed. Okay, now now this v1 minus v2 we will write it as small v. Okay, so now from velocity we will go to the momentum. So v1c we have, so the momentum p1c is actually m1 v1c, nothing but this. That will give you, if you multiply this expression with m1, so one m1 will come in the upper, I mean numerator, so that will make this mu, because m1 m2 by m1 plus m2 is mu, the reduced mass of this particular system. Okay, so that will be mu and small v. Similarly p2c, that will be m2 v2c, that is mu small v minus, as there is a minus sign. Okay, so you can see in your center of mass frame your momentum is 0, total momentum of the particular system is 0. It is very obvious because two are going with to exactly opposite sign, that makes that momentum of that particular system, I mean the, if we add up the momentum of these two mass, that will give me 0. It is in center of mass frame. Okay, but in the lap frame, your total momentum pl in the lap frame, that's why I have written it in l, m1 v1 plus m2 v2, because v1 v2 was your velocity of two particles with respect to the lap frame. Okay, now this is the thing, this is the lap frame velocity and this is the lap frame momentum, this is the center of mass momentum. Okay, now the important thing is we will do that. Okay, 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 so remember this image, we will need that. Now suppose I have a collision problem where a v1 mass, a v1 velocity, 1 means mass, associated mass is m1. Okay, it face some scattering or collision, whatever you say, and the final velocity is v1 dashed. Okay, sorry, and another mass v2, it will go as v2 dashed. So v1 v2 is the initial and v1 dashed v2 dashed are the final mass. So it is in the lap frame. Now Similarly, if you consider only this part of the system, I am converting the initial velocity in the center of mass frame. So you will get that v1 is directed in this way, v2 is directed in this way, and it is the v, which is the momentum of the center of mass before collision. So this is v2c, v1c. Okay, so v2c, v1c as the momentum of the particle before collision in the center of mass frame. And similarly, now we will convert this part in the center of mass frame. So here it was v1 and it was v1 dash, v2 dash. So v2 dash. So our center of mass frame velocity v. Now this is the v1c dashed, it is the v2c dashed. So v1c dashed and v2c dashed are the velocity of velocity after collision of two particles in the center of mass frame. Okay, so let me write it in a clearly. Initially v1 and v2 was in lap frame, v1c, v2c in center of mass frame, and final v1 dashed and v2 dashed are in lap frame, and v1c dashed and v2c dashed are in center of mass frame. Okay, so this we have done. I mean, we have converted our initial velocity and final velocity from lap frame to the center of mass frame. Now I will ask you to focus on this particular line, which is the velocity line of center of velocity line in the center of mass frame. I mean, this have the v2c, v1c and v1c dashed and v2c dashed in your center of mass frame. Okay, now we will superpose these two branch of this geometrical figure. Okay, so if we put this, it will be like this, and v1c and it is v2c. Okay, and if we put this, now it will take a form like this. Okay, so v1c dashed, v2c dashed. Okay, so now you can see the, I mean, let me take it here. Okay, and take this. Okay, okay, nice. So you can see this was the two situation, right? It was in lap frame before and after collision, and it was in the center of mass frame before and after collision. So you can see the main difference is, in the lap frame v1 was coming from a particular direction, from this direction, and then it was going into other direction, v1 dashed, and similarly v2 and v2 dash. But the interesting fact is that you can see in the center of mass frame, your the angle between your v2c and v2c dashed is actually theta, whereas v1c dashed and v1c is also theta. That means it is telling you that mass 2 is coming towards the center of mass, and after collision it is just scattered by a angle theta, whereas similarly mass 1 is also coming to your center of mass and it is just scattered by a angle theta. So the, I mean, complex collision here where we had no, I mean, we cannot tell priori that which direction v1 and v2 just will directed without doing the detailed calculation. But in center of mass frame we can say that my two velocity will just be rotated by a angle theta, and it is very simple to deal this type of collision problem in the center of mass coordinate, because here it is just a rotation of the velocity vectors, nothing more more than this. Whereas in the lab frame there are many things, and it is not so simple. So this is the main advantage of using the center of mass frame while calculating the collisions. And in the next day I will try to do a proper problem with these collisions, and you can see how easily you can do it. You can deal with the collision problem in this if you consider the center of mass frame instead of the lab frame. Okay, so this was the thing. Now any question or doubt? If not, then okay, then one thing I thought I could do. Okay, this one, yes. Okay, so the problem I will not do today because I have a meeting actually and I don't have much time today. So I will do the one problem associated with this center of mass in the next day, and the other central force problem I will also do. But one small thing I think I should, yeah. Okay, so this center of mass problem is I will do in the next class also, and I think you have understood why this particular problem is easy to deal in center of mass frame. Now coming to the central force problem, central force section, I will just do one small thing. I mean, how you can calculate the equation of a conic, that I will do very briefly. Okay, so suppose this is my coordinate system, this is my base, and I have a hyperbola like hyperbola like this. So the axis of my hyperbola, or the conic, I should not tell it the hyperbola. So axis of the conic is this, not this this one. This is not the axis, this is the axis. I mean, it is tilted with our taken coordinate system. Okay, so my drawing is not that good. Yeah, so you can think it like this. Okay, now how you can how you will define the trajectory which is taking this type of form, conic type of form. So we can do that very easily using some properties of this particular conic. So this is a line which is perpendicular to the axis, and it is called the semi-latus rectum, which has a height of L, and there is directrix of a particular directrix for every conic section. So the conic, the project, I mean the project, not exactly projectile, the position of a particle in the conic section can be defined by a properties. Yeah, so this is parallel to this line. Okay, this all are parallel to the axis. Okay, and yeah, so let us say it P, it is Q, P, it is P2, and it is P1, and it is tilted by an angle of phi 0. Okay, that means yes, phi 0, and this angle is phi, and let us tell this P0 point. P0, P1, P2, P3 are 4 points on that conic section. Okay, now there is something called eccentricity epsilon, which is a parameter of a particular conic section, and that is defined like this. So this is A3, A2 and A1, and it is the focus S. So SP2 by P2A2. So what is that SP2? So the S is the focus of that particular conic section, and P2 is the a position of the conic, and the ratio SP2, that is this distance, and this P2A2, that is means the distance from the directrix of that particular point, that should maintain a particular ratio epsilon, which we call eccentricity. So this can also be written as SP3 by P3A3, I mean this distance by this distance. Okay, so this ratio should be always maintained, whether it is P in the P2 point or P3 point or P1 point. So if it is P1 point, then we can write it as SP1 by P1A1. So this ratio is called the eccentricity, and this should be maintained in the, it is a property of the conic section. So this can be written as SP3 minus SP2 by P3A3 minus P2A2. This you can do. This has a name, I forgot some properties. So suppose if you have 2 by 4 equals to 4 by 8 is so half equals to 2 by 4 equals to 4 by 8. So you can write it as 4 minus 2 by 8 minus 4 also. So this is a property, and this will hold. Okay, so if you use this, now your SP2, this the SP3, this SP3 that I have written as L, which is the semi-latus rectum, and SP2, let us call it as R. This is a particular distance from the focus, and this P3A3, so P3A3 minus P2A2, so P3A3 minus P2A2, so this distance, I mean this total distance minus this small distance, that will give you this much distance, right? If you extrapolate that P2A2, so which is equals to SQ2. You can see this is the distance, SQ, sorry, not Q2. So if you write it L minus R, and this SQ you can write it as, if it is R, if this SP2 is R, and the angle between this SP2 and the our chosen coordinate system is phi, and the tilting is phi 0, that means this angle will be phi minus phi 0. Okay, so let me draw it. This was SP2, this was the angle, and this was SQ. So this angle is phi minus phi 0. So your SQ is SP2 time cos phi minus phi 0, right? So SQ is SP2 time cos phi minus phi 0, and your SP2 is R, which we have already taken. This R is a variable, phi minus phi 0. Okay, so epsilon. Now if you do everything, epsilon R cos phi minus phi 0 is equals to L minus R. So L is equals to R 1 plus epsilon cos phi minus phi 0, this one, and L by R is equals to 1 plus epsilon cos phi minus phi 0. Okay, so this is a very important equation. I mean, this we will use repeatedly in our central force problem. So this tells you the equation of a conic section with a semi-latus rectum length of L. Okay, so here I have defined that semi-latus rectum, which is this SP3, that is called the semi-latus rectum, and the length is L. So this is a equation we have to remember, and it is describes a branch, a group of conics depending on the values of epsilon, which is the eccentricity. So if your epsilon is less than 1, then it will be a ellipse. If it is 1, then parabola. If 0, then circle, and if you are then hyperbola. Okay, so this is important to remember, whether the epsilon, I mean anyhow you will whatever the way, when you will derive the equation of a conic, you will deal with the epsilon, and these properties of epsilon are important to remember. I mean this is one of the way to derive a equation very qualitatively, but you can do it in a very, I mean broad way also, to find the equation of the conic. But it just remember this particular two thing: L by R is equals to 1 plus E cos phi minus phi 0, the most important thing of this central force problem, which you will deal repeatedly, because by solving your equation you will always get a path of a that will follow the conic, whether it is ellipse, parabola, or hyperbola, or circle. Okay, so I will stop here today because I have some meeting. So if you have any question, you can ask me. And so Ipsita, you are asking about some Webb's book on the other day. So I found that I have read that book by a Indian author, that is J.C. Upadhyay. So you can follow that book. There are the Webb's problem. Also you can find the Webb's problem in very basic I mean differential equation book, because these are all differential solving of differential equation, nothing more than that. Yeah. Okay, so any question today? Okay, then we will meet next week on the same time. Okay, and thank you for joining. So bye.